Hi, folks. This is going to be a short, probably a 30-minute presentation, but I want to give some good news that we received last week. Primarily, ValAsta was awarded a patent out of the patent office for the use of ValAsta for the management of inflammatory disease resulting from radiation. This was initially developed for space travel, and I'm going to go through that aspect of this. But it does apply to us Earthlings here on Earth. We're not exposed to as much radiation as the astronauts are, but it has been approved, and it does look like it could be a key component in allowing us to go to Mars with the 3-year journey to and return without death as a result. So what I want to go through here is the types of radiation that astronauts would be exposed to. There's galactic cosmic rays that come from deep interstellar space. We're somewhat protected from those by the magnetic field of the Earth. It redirects those to the north and south poles. That's why we have an aurora borealis. There's also solar event particles. These are all the molecules of or atoms of the periodic chart that from hydrogen all the way up to uranium that come out of the sun, but they've been stripped of the electrons. These are high-speed nuclei of those atoms traveling at the speed of light. They're atomic bullets that's flying through. They are typically positively charged, so they're redirected also, and we're somewhat protected by the Earth's magnetic field. Those are the primary two. There's also light energy particles. Basically are the electrons that are flying off at the speed of light also, and I'm going to go through some of the radiation spectrum so we can see where they're placed. The galactic cosmic rays are called Kagers. They right now believe that they come from supernova explosions throughout the universe. They fly through space, very, very high energy, very difficult to manage. But I'm going to go through how we are now capable of understanding that and where ValAsta plays into that. This is out of NASA. It's called the Human Research Program, and they looked at the charged particles. This is what's keeping us from going to Mars. We knew this in 1994, and in a project called Artemis. As a matter of fact, the rocket going to the moon is called Artemis 1 because we initially did this work 92 through 94, and we knew that from a mechanical point of view, we could get to Mars, but the medical team had pretty much determined that, in fact, no one would survive. About 2 weeks outside the Van Allen belt, or the magnetic field protection of the Earth, the intense radiation would not only penetrate the spacecraft, but it would also cause irreparable damage and inflammatory disease in the astronauts, and the astronauts would probably expire within 2 weeks to a couple months. So we are not capable currently of going to Mars, but I am going to explain the 3 components that have to be looked at if we are going to go to Mars. Space radiation is definitely different than what we experience here on Earth. Here's just some things. Has sufficient energy to collide violently with the nuclei that make up shielding in human tissue. So this will cause, like ultraviolet radiation causes sunburns. That ultraviolet is radiation. And that in itself would be enough to cause skin damage, and we can see the long-term effects of cancer even with ultraviolet light reaching the Earth's surface. In addition to this, keep in mind these particles are moving at the speed of light. Even though they're very low mass, these things cause irreparable damage when they hit the DNA or the nuclei or protein inside the human body. Also, the spacecraft design is absolutely crucial. And so far from the designs that I've seen, none of them are capable of reaching Mars safely with the astronauts maintaining a health position that would allow them to even explore Mars. So as you can see, this is a major problem. Here's the radiation spectrum. Let's start all the way over to the left. Always keep in mind that the energy of electromagnetic fields or particles is equal to Planck's constant times the frequency. So the frequency, even though the wavelength is very long over on the left side of that curve, the frequency is very low. The frequency is nothing more than the number of humps per unit time. So it's in like hertz is reciprocal seconds. So you can see on the left side, very low energy, long wavelength. In those types of electromagnetic pulses, you can penetrate a huge distance. For example, if you're way out to past radio waves, you can get wavelengths that would actually penetrate the Earth. But as you move to the right, you see them get more and more frequent. You can see where visible light is on the spectrum. Infrared. These frequencies to the left are low energy, deep penetration. These frequencies to the right of the visible light, you can see where the frequencies really beginning to pick up. Gamma rays are up there pretty high. X-rays are up there pretty high, where they can actually go through the body. So there's quite a bit of intense energy at those high frequencies. But most of the frequencies that we're exposed to typically would penetrate maybe an inch of the skin at the most at these higher frequencies. And they're fairly, for example, Wi-Fi, or you can get into microwave radiation. Microwave radiation would penetrate into the skin, boil the water, cause the water molecules to vibrate, and create a burning sensation. That's how we heat things up in the microwave oven. The water molecules vibrate. But you can get to a point where these frequencies can get quite high, and they zing right through you. So all the way over where it says 10 to the 21 hertz, that's 21 zeros frequency. So this thing is really high energy, since energy is equal to Planck's constant times the frequency. The frequency is very high, you have intense energy. These are gamma rays, cosmic rays, and things that can penetrate right through the human body. We can look at things like X-rays. X-rays, if it hits a massive object like a bone or a mass, we can differentiate by the amount of X-rays that actually penetrate the body on the backside when we film it. So even X-rays, once it hits a massive object like a bone or something in our body, it won't penetrate it. But gamma rays, cosmic rays, SEPs traveling at the speed of light, these things can do it. How much radiation are astronauts exposed to? It's a lot. And this is the primary reason that there would not be an astronaut survive the trip to Mars. They would probably die within two months or so of exposure into the space between the Earth and Mars due to these typical radiations. The radiation is strong enough to cause degenerative diseases, inflammatory diseases, neurological disruptions. There's a report coming out shortly, if it hasn't already, NASA's going to release, that typically all astronauts expose detrimental effects due to their time in space, whether it's from Gemini or even up to the current space station and the trips to the moon, where there's no real protection at all against any forms of these high energy radiations. So here's an example. Radiations are exposed to ionizing radiation with effective doses in the range from 50 to 2,000 millisieverts. Millisieverts are a measurement of radiation. 1 millisievert of ionizing radiation is equivalent to about 3 chest x-rays. So that's like if you were to have 150 to 6,000 chest x-rays. That's a problem. So, and it's what's keeping us from making the trip to Mars currently. So how do we get to Mars? It would take from 9 to 12 months just to go from, we're going to go from the moon, by the way, from the moon to Mars. It'll be 1 year on the Mars surface. Mars has no magnetic field around its planet, very low atmosphere, so all the cosmic rays and solar event particles penetrate right to the Mars surface. It's going to expose all the astronauts. And then it's a 9 to 12 month return trip. So it's approximately 3 years if someone commits to going to Mars. Now, the problem we have with this is that the risk of exposure or the risk of imminent death right now is greater than 6%. To do a space mission requires a risk of imminent death to be less than 3%. So currently we are incapable of going to Mars. What would it take to make it to Mars? Well, it can be broken down strategically to 3 key components. We already have the technology, the mechanics, the engineering, the technology to get to Mars, so I'm not even going to consider that. Number 1 is the redirection of charged particles away from the astronauts using intense magnetic fields. We have to mimic what the Earth is doing. The magnetic field, north and south pole of the Earth's magnetic field, keeps us safe here on the surface. Mars does not have a magnetic field. The moon does not have a magnetic field. So we're pretty lucky that we have a magnetic field on the Earth to redirect these particles. Otherwise, there would be no life on this planet. The other one is construct a space vehicle from materials that absorb direct impact without spattering. There's only a certain number of materials that have this characteristic. These high-speed electron volt or radiation impacts are deadly. There's not a human being or maybe even a life form right now, unless it's protected or shielded, would ever survive a trip to Mars. The other one is, let's assume that some of the radiation that comes through this. So we've not been able, through redirection of using magnetic field, to get the particles away. We've not been successful in our materials of construction to absorb the radiation. Now the radiation has made it through and it impacts the astronaut. When it impacts the astronaut, it's going to fly through the astronaut, hit the nuclei, possibly the DNA, and it will cause radiation sickness or an inflammatory disease. When radiation hits a water molecule, which we are probably 75% water, the water will fragment into a hydroxyl free radical or a peroxyl form. In that form, we will be generating high levels of inflammatory free radicals called ROS, reactive oxygen species, throughout our bodies, and they then go rogue and begin to mutate the DNA. This will result in inflammatory disease, and probably within 3 to 6 months the astronauts would be so sick and terminal that they would not even make it to the surface of Mars. We have to find a way to reduce the radiation impact on the human being to eliminate these inflammatory diseases during the entire 3-year mission. So you can see that the design is going to be crucial. It is going to have to be toroidal, which means it's donut shape, and it's going to have to be wrapped in wire, run probably by a nuclear reactor to generate enough electricity to establish the intense magnetic field required to redirect these forms of radiation through the north and south pole of that donut. But the problem with these designs is that it's concentrating the magnetic or the electromagnetic particles towards the center where the astronauts typically are going to be resident. That's where they're going to be living. So the astronauts have to live in the donut. Well, there's some advantages to that because you can spin that donut and create artificial gravity. At the same time, they're being protected, and the radiation that's now focused right down the center could be concentrated enough to actually produce electricity. So there's some things here that we need to have a lot of research on to see if in fact we can have propulsion systems that can use the existing radiation in space and have enough capacitance that we can store that and use that as a possible propellant. But we now have the capability of collecting that electromagnetic radiation, store it, fire it as necessary. So the vehicle has to be designed in a donut or a flying saucer or a spinning gyroscope just to redirect most of the radiation away from the astronauts. So what I have here now is the construction of the vehicle, typical materials that we now know that will stop spalting or spattering of the metal: Kevlar, aluminum, carbon composites. These are the elements, the materials that spacecraft would have to be made of. The radiation that the astronauts will be exposed to will generate reactive oxygen species. Those species will cause inflammatory disease, cancer, similar to radiation sickness. And to date, only the antioxidants are the only materials that are effective in ROS reduction without any side effects. And ValAsta, this is what our patent was based on, is the most powerful antioxidant with no side effects that will remediate the reactive oxygen species generated from this type of radiation. This is not a trivial thing. We can now measure the inflammatory disease state of the astronauts, and now we can mitigate that. We have to have a way of sheltering them on board ship, keep them there until their CRP is reduced, and allow them then to return to activities on board. If you have any questions, I will be publishing the patent number when it's issued. This is so new that the patent office hasn't even issued the patent number yet. One other thing I wanted to mention was even people who have radiation treatments, because radiation treatments are very local. They can now target those if they're going after a cancer. They can get very specific. So that inflammatory response that your body's going to have to that radiation, high intensity radiation, killing the cancer, can be substantially mitigated because it's typically local inflammation. You don't want those free radicals that the radiation has created to get into your system because they will cause damage elsewhere. So ValAsta is a very, very good component to take because it deals with systemic inflammation, has very little effect at all on the radiation treatment itself because the radiation treatment is so focused and local that there's not even enough astaxanthin there to mitigate the damage and the effect of the radiation. But you do not want the free radicals generated from the radiation to become systemic and go throughout your body. ValAsta is going to mitigate that, stop that, and make sure that you all measure your C-reactive protein. That number should be less than 3. If it's greater than 3, get on ValAsta as quickly as you can. Get it trending down and stop this potential of you getting an inflammatory disease. With that, I'm going to close and thank you very much.